All right, let's talk about the Clausius inequality from week 3. Clausius established this ratio here. Sigma is equal to heat over temperature at the boundary. We'll get into what sigma is now, but we'll just say that is the ratio that we're working with. The dimensions behind this ratio is going to be kilojoules per Kelvin based on the units of heat and temperature. And when we're talking about that, imagine we're just looking at some system. We have a boundary, and that boundary has a temperature out here, TB, and there's also going to be some temperature inside T system. And if we want to look at that system, we can look at it in a differential element. And when we look at a differential element, we'll have some differential sigma. And this is just a differentiation del. It has the little curly Q on top because we are just talking about an infinitesimal element. It's going to keep the exact same dimensions. So again, we're just going to look right there at an infinitesimal element on the boundary. So if we're looking at the temperature of the system and the temperature of the boundary, we can start asking questions. Is there a gradient here? That's what this table is going to start telling us. If there is no gradient, as in there is the same temperature in the system as the boundary, then Q, as in the heat transfer, is going to be 0, right? Because if they are the same temperature, there is no gradient for the heat to transfer over. When we look at that Clausius inequality, the ratio was our Q over T. So if you have Q is equal to 0, then sigma is also going to be equal to 0. Now, if the system is hotter than the boundary temperature, then we will have heat transfer. Because heat is leaving the system from that transfer, you're going to have Q is some number less than 0. It's negative. Heat is moving in a direction away from the system. Following the inequality, we will also see that sigma is less than 0. This last one's a little tricky. If the boundary temperature is greater than the system temperature, then you would have, theoretically, Q, or heat, moving into the system. The problem is that's not going to happen. This cycle can't take place because there is no temperature gradient for the thermal energy to be able to do work. This is why the Clausius inequality can be written as Q over T is less than or equal to 0, which is what we discussed in class, was this right here. A second ago, we were looking at these differential elements. And if you watch the video on cyclic integrals, we can take the summation of all these differential elements with a cyclic integral like this. And this is exactly what we saw in class, where this is going to be less than or equal to 0. And we set that up because now we can look at sigma, or the Clausius inequality, and begin to interpret whether or not the process is reversible, irreversible, or if it will not take place. The last thing I want to bring up is that we can see that temperature and heat transfer are properties of a system. That also shows that sigma is going to be a property. When sigma is a property, we're going to just rename it. right now it's that ratio, but in all future problems, we're going to say that sigma is equal to entropy generated in a cycle. So whenever we're moving around through our Carnot cycle, we can look at the entropy generated across the cycle. So in summary, this is our Clausius inequality, and we are just looking at how there is a temperature gradient that affects heat transfer, and whether or not that ratio or the Clausius inequality is equal to 0 or less than 0 tells us whether or not the process is reversible or irreversible. And the point of including this cyclic integral is just because this inequality is taking differential elements around the boundary, and we need to sum all of those up to understand the system.